Okay, so I'm going to give you a very brief status of the muon G-2 theory and experiment and tell you what is going on with the lattice right now. So first we have to pay homage to the experiments. So very beautiful experiments that started, a long time ago in CERN, then went to Brookhaven and are now at Fermilab. And these have provided us with an excellent opportunity for maybe a discovery. So let me start with the hadronic light by light scattering contribution to the muon G-2 because it's easier to get out of the way. This is subleading in the fine structure because there's 3 photons connecting the hadronic blob. But the size of the hadronic contribution from light by light is about the size of the current discrepancy between theory and experiment. And the uncertainty is pretty large, or it was pretty large. So we have to make sure that we have this under control. And the good news is it seems to be under control. So for a long time, we used what's known as the Glasgow Consensus for the hadronic light by light contribution, which was based on models and effective field theory. But now there are data-driven approaches, just much like the hadronic vacuum polarization, and the errors are really under much better control. And we also have first principles lattice QCD calculations. And if you take these 2 into account, and so this is from the muon G-2 theory initiative white paper in 2020, then you get this answer for the hadronic light by light contribution. And what this means is that, basically light by light's not going to solve our problems. It's not the reason for an apparent discrepancy, if there is one, between theory and experiment. Okay, so now let me move on to the hadronic vacuum polarization, which is the leading hadronic contribution. And I'm just going to basically tell you about how we do the lattice calculation. So most of you are probably used to, calculating this contribution in momentum space, where, we take the hadronic vacuum polarization, we convolve it with some known one-loop QED integral, and that gives us the hadronic contribution. So on the lattice, we're interested in, we're working with quarks and gluons. So, there's actually 2 different types of diagrams that we need to calculate, so-called quark connected diagram and the so-called quark disconnected diagram, where the quark loops here are only connected by gluons. It turns out that this is by far the dominant contribution. This is mostly what I'll focus on today. We actually have to go one higher order in the fine structure, because if we want to compare to the data-driven result, we need these contributions, because they can't get rid of these in their analysis. Okay, so for the lattice, we work in Euclidean time, Euclidean space, and it's much easier for us, instead of working in momentum space, to work in Euclidean space-time. Really, what we'll be interested in is the Euclidean time separation between 2 electromagnetic currents. And, just like you can get this contribution by doing this integral over momentum, well, in Euclidean time, we just have to integrate over the Euclidean time. Where again, what we're going to measure on the lattice is this correlation function for the electromagnetic currents, but in Euclidean time, and then multiply it by some known function that comes from the QED part of the diagram. And so that's the way we're going to approach the problem. So, of course, we're working on the lattice. It's a 4-dimensional Euclidean spacetime lattice with some lattice spacing and finite size. So we have to do the calculation over and over again with smaller lattice spacings and larger boxes and so on, and extrapolate to the continuum and infinite volume. And this is just a typical example of what that looks like in a lattice calculation. So the blue points here are the lattice values. The magenta band here comes from somebody's calculation of the R ratio. And the points to keep in mind are, you know, in a large range of Euclidean times, the lattice does quite well. But as we get to large times, fluctuations from the dominant 2 pion state mean that the correlation function becomes noisy, and so that's hard to deal with. And also at very short times, of course, you know, the vacuum polarization realizes, hey, I'm on a lattice, I'm not in the continuum, and there are big discretization effects. So here's the lightning summary of where the hadronic vacuum polarization contribution stands. And, you know, this basically comes from, again, the muon G-2 theory initiative circa summer of 2020. At that time, this was the lattice value, which has a fairly respectable error, but, you know, it's still relatively large. And this should be compared to the data-driven approach, which comes in at a central value that's somewhat smaller than the lattice average and a much smaller error, so about a factor of 4 here. And so the lattice average comes from these blue points here, and the data-driven one basically comes from these 2 red points here at the top, with a little extra from some other areas. And then after the white paper was published, one lattice collaboration, the BMW collaboration, came along with a lattice calculation with a quoted error that's on the same order as the data-driven approach, but still with a somewhat higher value. And so if you take the difference between the lattice value and the data-driven value, everything is completely consistent. And if you take the difference between BMW and the data-driven value, then things are off a little bit. There's some tension here. But then if you compare those to the experiment, of course, what you all know is if you take the white paper value and the data-driven HVP, you get a 4.2 standard deviation difference with experiment, whereas if you take BMW, it's only 1.5. And so that's where we are now, and that's what we're trying to understand. So to do that, on the lattice side, what we're going to do is we're going to break up the problem into smaller chunks and attack the easy ones first and leave the harder ones for later. And so what we're going to do is we're going to break up that sum over Euclidean times into 3 chunks: a short distance piece, an intermediate distance piece, and a long distance piece. And we do that just by inserting a smooth step function or filter into the integral, which cuts off the regions we don't want and leaves the regions we want. And that's what these windows look like. So there's the short distance window, there's the long distance window, and this is an intermediate distance window. And this is what they look like in momentum space or energy space. And so if you did that for the R ratio data, again, you have the total and you have the short distance contribution, and then you have a long distance contribution. And again, it looks like this in energy space. So again, the reason we're doing that in the lattice is because we can do this intermediate range much easier right now than we can this long distance part where the fluctuations are quite large. And again, the short distance part where taking the continuum limit, where the lattice discretization errors are quite large. And this is, again, the same sort of figure I showed, but it's new updated data from the RBC collaboration. So let me start with so-called staggered fermions. For those of you who aren't familiar with lattice fermions, they come in different shapes and sizes. And staggered fermions have the benefit that they're inexpensive relatively to use. But they have the drawback that they have extra degrees of freedom than you have in the continuum called tastes. Because they actually come from the doubling problem. They're like extra flavors, but they're called tastes. And these tastes, their contribution vanishes in the continuum limit. But at finite lattice spacing, they can have quite large contributions that we have to account for. And so it's typical in lattice calculations with staggered fermions to actually calculate the taste breaking effects in effective field theory and even effective field theory plus models that include a vector meson and subtract them before you take the continuum limit. And then the idea is that taking the continuum limit will be easier. Okay. So this is the BMW collaboration's calculation of this short distance window, the contribution to A mu from the range, say 0.4 Fermi to 1 Fermi. And this was the situation around the time of the white paper, okay? So here's the R ratio value for the window, and here's BMW without doing these taste corrections. And they extrapolate to some, would extrapolate to some rather high value. And then with the taste breaking, you see the lattice discretization effects appear to be smaller, but they're still not zero. And so when you extrapolate, you get some number up here. And this number is about 4 standard deviations different from the R ratio value. This is another collaboration using staggered fermions. And again, here are the uncorrected data in black, and then various corrections, the so-called S-row model, and then next to leading order chiral perturbation theory, and next to leading order chiral perturbation theory. And again, they give somewhat different answers, but they don't seem to agree with the R ratio value. And then finally, there's an update from the Fermilab lattice, HPQCD and Milk collaborations. By the way, these two collaborations are using the same lattices and almost the same Dirac operator on the lattice, but they're slightly different. And here they're using conserved currents for the vector, for the electromagnetic currents. And here they're using so-called local currents that aren't exactly conserved on the lattice, but those are details. So it means that they can have different order A squared effects, but they have to agree in the continuum limit if everyone's doing it right. Okay, so this is the new updated value from FHM, and they have quite small errors, but at the moment they haven't unblinded. So we don't know if this really is going to be consistent with these staggered calculations or consistent with the R ratio. And one of the important things to notice here is that we're systematics dominated at this point for the window, not statistics dominated. And the question is, are these corrections really reliable at this level? Because we need fantastic precision. So those are the kinds of things that we're asking ourselves and looking into at the moment. Now, there are some discretizations that don't have these tastes. They don't have tastes, and so they don't have taste violations. Okay, good. One of them is the RBC collaboration. They use something called domain wall fermions, which, if you know anything about lattice, are Wilson-like fermions. So there's no taste, but they're more expensive to compute with. So there's trade-offs. But it's again, at the time of the white paper, the domain wall fermions, which were only done at 2 lattice spacings so far, because they're expensive, seem to be consistent with a lower value for this window quantity, which in fact is consistent with the R ratio value. So the question is, what happens when you add a 3rd lattice spacing? It's at a smaller value. Is it still consistent, or does it become more consistent with the staggered fermion calculations? And we don't have the answer to that yet, but that's what we're really working on. And in fact, we do have an error bar for that calculation, and it's very, very tiny. It's on the order of per mil. But again, this is an analysis that's ongoing, and it's still blinded, so we don't know what the answer is yet. Hopefully, very soon. And again, even for domain wall in this case now, you're no longer statistics dominated. You're going to be dominated by systematics. Whoops. Okay, no time left. So this is my last slide. Because things are becoming statistics dominated, it's also incredibly important now to be able to precisely determine things like the lattice spacing. Not only to do the extrapolation, but the lattice spacing actually affects the value of A mu, because the muon mass, which is a physical scale, enters in this kernel function. And so the lattice spacing enters, and it enters about a factor of 2 times this scale setting uncertainty. And these are sort of the state-of-the-art scale setting uncertainties, and those have to come down as well to the per mil level if we're going to reach our precision goals. And we're, you know, the RBC collaboration, for example, is on track. So this will be a scale setting determination on that fine lattice that's about a per mil. Okay, you know, this is just what I said. I didn't talk about this stuff, but since I'm out of time, I'll just end with that. But also tell you that there are 2 meetings coming up this year where hopefully new results will be announced. So, you know, keep your ears open, you know, around June and maybe in September. So thank you very much.
Thank you, Tom, for this very clear talk. Are there questions from the room?
I can't resist making a stupid comment. The one time I encountered Schwinger, he railed against the stupidity of QCD with quarks and gluons. How could anybody believe that? So when you talk about this at his celebration of the anniversary of his birth, is he going to roll in his grave?
Oh.
We're going to learn all about this stuff.
He's not going to roll, he's going to precess. Can I ask a question too?
Sure.
Sorry, this is Lance Dixon. You showed a plot there that showed extrapolations for NLO and NNLO.
Right.
Chiral perturbation theory, and NNLO is steeper than NLO. Should we be worried about this?
Yeah, I mean, that goes to this question about, you know, are they reliable? So here, there's a good reason for this big jump from NLO to NNLO, because at that point, the rho meson comes in from a counter term at NNLO, which is not there in NLO. So that's why the big jump is there. But you know, for this window from the point of view of chiral perturbation theory is, you could say it's kind of a short distance quantity, because you know, you go down to fairly short distances. And so chiral perturbation theory may not be reliable.
Thanks.
There's good reason to believe it's reliable for the entire contribution.
Hi, Tom. This is
Hi.
Aida El-Khadra, and I just wanted to follow up on this discussion. As I know you agree as well, what is important about also making sure that those corrections are well understood is to see that whether or not you add these corrections, if you are in the range where these are small enough that you see that there's consistency between the continuum limits. And you know, if there's not consistency, then that has to inform the error, the systematic error, which is the point that you were making. I mean, that's the claim of for BMW is that they can actually, for the intermediate window, they can extrapolate their data without including the corrections. And the concern is that for the total AMU, they cannot do that because their case-breaking corrections are so large that they're not describable as just A squared terms. And even without, I mean, you can see that in their flavor of, pardon the pun, of staggered fermion, you know, it's just larger. So I think there's a lot to be learned just from having different flavors of staggered fermions as well to really understand that.
Yeah, it's hard to tell from this plot, but it looks like if you extrapolate the uncorrected data, right, it's even quite a bit higher than the, I don't know if these are consistent or not, but you say they, in their paper, they say they are. You know, to me, it looks a little problematic, but I would just add to what you just said that for BMW, their largest error, part of their error comes just from this, you know, the difference they get depending on how they do the corrections.
Hi, Patrick Mead. If you go back to the diagrams that you are computing for the lattice, you mentioned that you have to go for HVP one order higher to kind of match the data-driven in the weak coupling. But can you say a little bit more about this? Because I thought the point of the data-driven is they're trying to remove as much of the ISR as possible. And I mean, there's still this ambiguity, but
This isn't that ambiguity.
okay,
I mean,
so that's not that ambiguity.
This is just a real contribution that they can't get rid of.
Okay.
Yeah.
Okay. Thank you.
Just a very quick question. I was actually wondering if you could hear your thoughts about the hadronic vacuum polarization contribution and the recent discussion of the fact that the tension between standard model measurement might be reduced. I was thinking maybe you can share your thoughts.
Sorry, reduced because why?
The hadronic vacuum polarization contribution to muon G-2 and the fact that the tension between standard model and data is potentially reduced. There was this paper from 2020 on the topic. I was wondering if you can hear your thoughts about this.
What do you think if BMW was right?
Oh, I mean, I guess I don't have a, I don't want to say something publicly. I mean, it's hard for me to believe if everybody does their job that we won't eventually agree. I mean, the data-driven people have been doing this for decades, and it's hard to see where they might have messed up. And, BMW is certainly a very good collaboration, just like the other ones in the community. So I think in the end, we're gonna be able to resolve things, but we haven't done it yet, so.
Okay, thank you very much. We have actually to move to the next talk. Thank you very much. Thanks again.